Hello, let's take a look at this practice test that you did last week. Um, we're looking at a titration of this one's a weak acid with a strong base. So when you do your ice tables, if it's just the acid and the conjugate, you aren't using the Henderson-Hasselbalch equation. If excess NaOH is the only thing present, then that will dominate the pH. If the conjugate is the only thing present, then you will have to consider that reacting with water for the reaction. And that's what you got going on. And so let's take a look at, why are you not moving for me? There we go. Now we're scrolling. So we have 30 milliliters of 0.1 molar. So multiply those and you get 3 millimoles. By 0.10 molar sodium hydroxide. So the first problem asks you to take a look of when you have added no base. So all you have is the acid dissociation to consider for the pH. So again, we start off with 0.1 molar. I go ahead and use the concentration here. Subtract X, add X to the ions. And so you get that the Ka is equal to X squared all over the original concentration of the HA. And the Ka here is so small, yes, you can estimate. And so you're going to basically get that X squared all over 0.10 molar is equal to the Ka. So when you do all of that arithmetic, you get that X is equal to 2.4 times 10 to the minus third. Well, as you can see, X is the hydrogen ion concentration. So take the negative log of that number, and that gives you the pH. Then for part B, you are given 10 milliliters of the base. And so I took 10 times 0.1, and that gave me 1 millimole. I still have my 3 millimoles. That was my 30 milliliters times the 0.1 mole. That's how I got that number. And so hydroxide is the limiting reactant. So it's going to be completely consumed. And so you're going to have 0 of that, 2 of the acid, and 1 millimole of the conjugate. And so we're going to use Henderson-Hasselbalch since we have the acid and the conjugate present. And so we're going to take the Ka of 6 times 10 to the minus fifth and take the negative log of that number. And that gives me the 4.22. And I'm going to then find the negative log of the ratio of 0.1 divided, or 1 divided by 2, which is 0.5. And so that gives you a log of negative 0.3. Since it's less than 1, it's going to be negative. And so you subtract them and you get a pH of 3.92. For part C, you have equal molar amounts of acid and base. So you're only going to have remaining the conjugate. So you have the conjugate reaction with water to consider. And you know that a weak acid has a strong conjugate base. So what's going to happen when it reacts with water is the conjugate is going to form hydroxide. So you know you're going to get a pH greater than 7 already. And so you have 3 millimoles of A minus. Go ahead and change that over to concentration at this point. So I divide it by, I added 30 milliliters of acid, 30 milliliters of base. So I'm at 60 milliliters total volume. And so I divide that by the 60 milliliters. And 3 divided by 60 gives me 0.05. And so I also have to find the Kb. So I take Kw, which is 1 times 10 to the minus 14th, divided by the Ka, the 6 times 10 to the minus 5th. And I get Ka is 1.7 times 10 to the minus 10th. And that's going to get equal X squared all over 0.05. So I take 0.05 times the Kb and square root it. And that gives me a hydroxide ion concentration of 2.9. That gives me a pOH of 5.53. and a pH of 8.47. For part D, I have an excess of hydroxide here. So this time the limiting reactant is the acid. So there's no acid remaining. And so I have hydroxide and the conjugate. Well, the hydroxide is much stronger than the conjugate, even though it's a strong conjugate base, it's much stronger. It's going to overrule the pH. So all I have to do is say, okay, I have 1 millimole, a total of 70 milliliters. That's the 30 milliliters of acid plus the 40 milliliters of base that I added. That's where I get the 70 milliliters. I divide those two, and that gives me that concentration of hydroxide, which gives me that POH. 14 minus that number gives me the pH of 12.15. So you just walked through a titration problem. And then the next problem, number 4, is about KSP. So the first thing you want to do with a KSP is you want to look at the chemical. So when you look at the chemical, and you can see this one is silver chromate. So it's going to form 2 silver ions and 1 chromate. So that means that this concentration would be 2x to 1x in comparison. And so you can see that you're going to take that 2x and square it. And so 2x squared is 4x squared. And then you're multiplying it times, so you're taking 2x quantity squared times x. And that's how I get the 4x cubed. And so I'm going to take 1.9 times 10 to the minus 12, divide it by 4, and then cube root it to get this value for the molarity. Number 5, calculate the ratio of sodium fluoride to hydrofluoric acid to get a pH of 3.5. You're making a buffer solution. You find that Ka is equal to 7.2 times 10 to the minus 4th. I got that out of the back of the book is where I found that. And so I take the negative log of that number, and that's what goes there. The pH here, and I'm just going to go ahead and say that's 3.50 for SIGs. And then that's plus. And what I do is I change this ratio to just a single variable so I can solve for that ratio variable because that's what you're asked to calculate. And so I'm going to subtract 3.15 from both sides, and that gives me my 0.35, and that's equal to log x. So take 10 to the 0.35, giving you 2.24. And that 2.24 means that the numerator, the acetate, I'm sorry, it's not acetate ion. In this case, it's the fluoride ion, is going to have to be 2.4 times more concentrated than hydrofluoric acid. So you can come up with all kinds of concentrations that will work. It is not going to be a single concentration answer. It's just going to be that whenever you divide the sodium by the HF, it has to equal 2.24. So you can see if I divide these two, it's going to give me 2.24. If I divide these two, it's going to give me 2.24. And then I even did one more down here. If I divide that, it's going to give me 2.24. So here's just a few possibilities of the possible concentrations that will give me that pH. And of course, the beauty of being able to do this is there are certain times you want something to exist at a certain pH. And so putting it in a buffer system will do that. And so that's the power of knowing how to use buffers. Hope this helped. Hope you're ready for the test on Thursday. It'll be kind of in the same format where I'm going to make sure that you are at the point to be exposed to the test, and you will have to email me to request a password. Talk to you later.